What is joint space in robot kinematics? Imagine trying to move a robotic arm smoothly from one point to another. How does the robot know how to position each joint to reach exactly where you want? That's where joint space comes into play. It's like a map of all the possible ways a robot can position its joints. Each joint, whether it rotates or slides, has a range of motion. When you combine all these ranges, you get a space that describes every possible configuration of the robot. Think of it as a big, multi-dimensional grid where each point represents a specific pose of the robot. If you have a robot with 6 joints, its joint space is 6-dimensional, with each axis representing one joint's position or angle. This space makes controlling the robot easier because you can tell it to move from one point to another within this grid. Instead of thinking about the position of the end of the arm, you think about how each joint should move. Moving in joint space is often simpler because the joints are the actuated parts you control directly. To get the robot's end effector, like a gripper or tool, to a specific spot in the real world, you need to convert between joint space and the position in the physical environment, which is called Cartesian space. Forward kinematics helps you find the position of the end effector when you know the joint angles. Inverse kinematics does the opposite. It calculates the joint angles needed to reach a specific point in space. This conversion is essential for tasks like welding, painting, or assembly, where precise movement along a straight line or specific path is needed. When planning a robot's movement, you can choose to work directly in joint space for quick, simple motions, or in Cartesian space for precise, controlled paths. For example, moving a robot's arm to pick up an object might be done in joint space, but guiding the end effector along a straight line requires planning in Cartesian space, and then translating that into joint movements. In essence, joint space is the fundamental framework that describes all possible robot configurations. It helps engineers and programmers control the robot's movements efficiently and accurately. Understanding how joint space relates to the physical world through kinematic calculations is key to designing better robots and making them perform complex tasks with ease.